Do we need a new programming language for space? When people picture the future of space exploration, they usually imagine bigger rockets, better engines, or new materials that can survive extreme conditions. Software almost never comes up. It feels secondary, invisible, like something that just works in the background. But more and more, space missions aren't hitting their limits because of hardware. They're hitting them because of software. Not because space computers are weak, but because the code running on them was never designed for an environment like space in the first place. There's an uncomfortable reality behind this. Spacecraft hardware often lasts longer than the software it runs. Radiation-hardened processors are slow by Earth standards, but they're built to survive. Many probes and satellites keep operating for years, sometimes decades, beyond what anyone expected. The software doesn't age nearly as well. Programming languages change. Libraries become obsolete. Development tools evolve. Assumptions that made sense on Earth quietly stop being true. Once a spacecraft launches, most of that software is frozen in time. Bugs discovered later may never be fixed. Wrong assumptions may never be corrected. And increasingly, those limitations define what a mission can and cannot do. That's where the question starts to surface. Do we need a new programming language for space, or is that missing the point? To answer that, it helps to look at what we already use. Most space software today is written in C, C++, or Ada, with newer experiments exploring Rust. These languages weren't chosen for being trendy or expressive. They were chosen because they're predictable, well understood, and give engineers tight control over how the system behaves. Yet all of them carry the same hidden assumption. They were designed for an environment that space simply does not provide. On Earth, software exists in a forgiving world. If a program crashes, it can usually be restarted. If memory is corrupted, the operating system may catch it. If a bug slips through, a patch can be deployed. There's an underlying expectation that failure is rare and recoverable. In space, none of that is guaranteed. Radiation can flip individual bits in memory. Instructions can change silently. Sensors can return values that look valid but are physically wrong. Timing drifts, components degrade. The environment itself is actively hostile to reliable computation. Most programming languages quietly assume that memory is stable and execution is deterministic. In space, both assumptions break down. To compensate, engineers add layers of redundancy, checks, and defensive code by hand. That approach works, but it's fragile. It's expensive, and as systems grow more complex, it becomes harder to reason about what the software will actually do when things go wrong. At this point, it's tempting to think the answer is simply a safer language. Languages like Ada and Rust eliminate entire classes of errors. They prevent many memory bugs and undefined behaviors before the code ever runs. That's a real improvement, and it matters. But it doesn't solve the deeper problem. Even perfectly safe code can make incorrect assumptions about the world. It can enter states that are logically valid but physically impossible. It can fail catastrophically when the environment behaves in ways the programmer didn't anticipate. Language-level safety helps, but it doesn't make software resilient. Because space software doesn't just need to be correct, it needs to survive failure. That realization shifts the question entirely. The real limitation isn't syntax or type systems, it's the way we think about software. Most programming models treat failure as an exception. Something rare, something to be handled and moved past. In space, failure is the default. Bits flip, sensors lie, subsystems degrade gradually or fail partially. Timing assumptions break without warning. So future space systems are moving toward a different philosophy. One where software assumes it will fail and is designed around that fact from the beginning. Logic is implemented multiple times in independent ways. Systems constantly monitor and cross-check themselves. Decisions are made by voting rather than trust. Software modules can be isolated, restarted, or replaced while the mission is still running. In this model, no single program is trusted completely, not even its own outputs. Programming languages can support this kind of design, but they can't enforce it on their own. Still, this pressure may lead to new kinds of languages. Not flashy ones, and not necessarily more expressive ones, but languages built around formal verification, runtime checking, explicit models of failure, and deterministic behavior under uncertainty. Languages where uncertainty isn't treated as an edge case, but as a core feature. Even then, the language will only be part of the solution. Space missions don't fail because of a missing keyword or an unsafe pointer. They fail because of unexpected interactions between software, hardware, and reality itself. So do we need a new programming language for space? Maybe. But more than that, we need software architectures that expect failure, systems that can adapt after launch, redundancy at every level, and a mindset that treats software as a critical scientific instrument rather than a supporting tool. Space exploration is becoming software limited, not because we lack intelligence, but because we're pushing systems into environments they were never meant for. The future of space won't just be written in better code. It will be written in software that knows it can be wrong and keeps going anyway.